Hi, in this session we are going to discuss guidelines for asymptotic analysis. By using these guidelines, we can find the time complexity of the algorithm easily. Whatever the discussion that we are going to do is applicable for space complexity as well. By using similar guidelines, the space complexity of the algorithm can be calculated. Now let us see the guidelines one by one. Constant. When do we say the given algorithm or code has the constant running time or time complexity? Let us consider this simple function. Here n is the input for this function. Let us print the value of I. In this function, the for loop is getting executed for 10 times, that is 0 to 9. Whatever will be the input value. The number of iterations of the for loop are not dependent on the input n. If the iterations are not varying in terms of n, we can say the running time of the algorithm is constant and we represent with order of 1. So the time complexity of this code is order of 1. Let us say instead of 10, what if we put 100? Whether it is 10, 100 or 200 doesn't matter. As long as it is constant and not varying in terms of n, we can say the time complexity of the algorithm is constant and it is same order of 1 for this algorithm as well. Now let us see the next one, loops. Simple loops. If the code has loops, something similar to that, instead of having constants, let us say we have n here. In this case, the number of iterations of the for loop are dependent on input, and since it is running in terms of input, we can say the running time of the algorithm is whatever the running time of the statements within the loop, let us say this is constant, multiplied by the length of the for loop. That means the number of iterations of the for loop, say n. So the complexity of this code is order of n, since we usually ignore the constants. If it is varying in terms of input, we can say the running time of the algorithm is order of n for the loop section like this. Now let us consider the small variant of this one. Instead of printf, let us add break statement. In this case, even though the for loop seems to be dependent on the input, but after the first iteration, we are coming out of the loop because of the break statement. So we should carefully look at what is there inside the for loop, to see how many times the loop is getting executed. We cannot go blindly by looking at the iteration length, for loop length. We have to see what is there inside the loop, actually, what statements are there inside the loop. So for this code, whatever may be the n value, since you are coming out of the loop every time after the first iteration, we can say the running time of the algorithm is order of 1. Since we are coming out of the loop after the first iteration itself. Now let us consider the next one, nested loops. Let us have nested for loop here. Let us say some print statements we have here. If we have nested loop in the given algorithm or code, the complexity of the algorithm can be calculated as complexity of the statements within the loop, let us say that is constant, multiplied by size of the each for loop in the reverse direction. Size of this one is n, size of this one is n. So the overall time complexity is Cn square, which we can represent as order of n square. So the time complexity of this code is order of n square. time complexity of the statements within the inner loop multiplied by size of the each for loop. We will get the overall time complexity of the code. Now let us make small change to this one. What is the time complexity of this code? This loop is getting executed for n times. This also seems to be executed for n times. But because of the break statement, it is executing only for one time. So, the overall time complexity of this one is, this is constant, multiplied by, since we are executing only for one time, 1 into size of this for loop n. So, the overall time complexity of this code is order of n. We have to see how many times the loops are getting executed. Based on that, we can multiply the size of the each for loop with the time complexity of the statements within the for loop. Now let us see the next one, sequential. Now let us add another for loop after the nested for loop. If the given algorithm has multiple code snippets, multiple components, one nested for loop and another simpler for loop or any other problem statements, we have to take running time of the each statement and sum them. So the overall running time of this code is, these two will take constant, since we already seen that this is n square and for this one n. So c plus n square plus n, which can be written as order of n square, because we are approximating the smaller values to the bigger value. So the overall time complexity of this code is order of n square. So in the case of sequential, if the algorithm has multiple statements, we have to take the running time of each statement, sum them, and whichever is the maximum, we have to approximate to that. Now let us see the conditional one. Let me make small change to this function or code. For simplicity, let us ignore this constant. If n is less than 100, let us say you are executing this if part, else we are executing the else part. So for the input n is less than 100, we are going to execute this block. If it is greater than 100, we are going to execute the else part. If the code has conditional statements like this, we have to take each and every possibility of the code path. That means, here one possibility is if n is less than 100, we have one possibility. And the second one is if it is greater than 100. To calculate the running time of the conditional statements, first we have to take the running time of the condition itself. Let us assume the running time of the condition is constant because it is a simple expression. Constant plus whatever the running time of the if part. Since we already seen that is n square, so c plus n square. Similarly, in this case, running time of the constant. So the condition running time is common to both if part as well as else part. So we have to take that into consideration in every case. Plus running time of the else part. Since it is n, you can sum that. Among these possibilities, since n square is bigger than n, we can say this is the worst case and this is the best case. On what inputs we are going to this one? On what inputs we are going to the if part? So the worst case running time of this algorithm is order of n square, and the best case is order of n. So in the case of conditional statements, we have to take the running time of the condition plus either if part or else part, whichever is bigger, if you want to calculate the worst case time complexity. Now let us make small change to this condition. Let us say instead of simple expression, we have a function where we are calling this one. Let me see, some different function you are going to call here. Assume the running time of this one is NQ. That means it is doing some calculations and giving the final result, whether it is true or false. So in this case, the running time of the expression is n cube plus the running time of the if part, that is n square. In this case, running time of the condition n cube plus n. If you observe these two, the running time of the if part, running time of the else part, both are same, which are nothing but order of n cube in both the cases. So in this case, we can say the best case complexity and worst case complexity are same. The only thing that we need to observe carefully is how much time the condition is taking, and that we have to take into consideration of both if part as well as else part. Let us see the next guideline, logarithmic. When do we say the given algorithm has logarithmic time complexity? For example, binary search, merge sort, heap sort, these are all associated with logarithmic time complexity. When do we get such complexities? Let us consider this simple function. With input n, I is less than n, multiplied by 2 every time. Here we are comparing I value with n, and I is getting doubled every iteration. Since we are doubling the I value every time, definitely the number of executions of this while loop, number of iterations of the while loop are less than n. But what is that value? How do we calculate that? Let us assume we are coming out of the while loop at kth iteration. Since we don't know at what iteration we are coming out of the loop, let us assume the iteration is k. At first iteration, the value of I is 1. In the second iteration, because of the doubling, it becomes 2. Next iteration it will be 4, 8, 16. It is nothing but 2 power 0, 2 power 1, 2 power 2. And at kth iteration, we can assume the value of I is 2 power k, approximately. Since we are assuming we are coming out of the loop at kth iteration, the value of I is 2 power k. If it is greater than or equal to n, if it is less than n, we will be still executing the while loop. Since we are coming out of the loop at kth iteration, it should be greater than or equal to n. So as soon as it is true, we are coming out of the loop. Let us take logarithm on both sides. With base 2. Based on logarithmic properties, we can move the k here. As we know, log 2 base 2 is 1. So the number of iterations of this while loop is k, which is represented in terms of n as log n base 2. So the overall complexity of this code is log n base 2. So if you carefully observe this code, because of the doubling approach, we are getting log n base 2. Instead of 2, if you put 3, what happens? On the similar lines, at kth iteration, the value of I will be 3 power k, and overall we will be getting the complexity as log n base 3. If it is 4, we will be getting log n base 4. If it is 5, we will be getting log n base 5. Now let us consider the small variant of the same code Instead of starting at 1, we'll be starting at n. Similar code, while I greater than 0, I is equal to I by 2. The number of iterations of this while loop and this while loop are exactly same. Here we are starting at 1, we are going till n. Here we are starting at n, we are going till 0. Whether we are doubling by 2 or decrement by 2, divided by 2, the number of iterations are same. The total number of executions of the both while loops are same. So for this code also, the time complexity is same, that is nothing but order of log n base 2. Here instead of 2, if we divide with 3, it will be log n base 3. If we divide with 4, it will be log n base 4. Now let us see, when do we get n log n? Let us say I am adding one for loop, I is equal to 0, let us say j is equal to 0, j is less than n, j plus plus. This while loop is inside the for loop. Same is applicable for others as well. The overall time complexity of this while loop is log n base 2, which we already seen. If they have nested loops, we have to calculate the running time of the inner loop multiplied by the number of iterations of the outer loop. So here we have n. We have inner loop complexity as n log n base 2. Overall time complexity is n log n base 2. If we add another for loop, it will be n square log n base 2. If you make it as 3, n log n base 3. Now let us see the guideline square root n. When do we say the given algorithm has square root complexity? They are similar to logarithmic. There are multiple ways of getting the square root and complexity. In the logarithmic running time, we have seen 2 code snippets where both are giving the same complexity log n base 2. Here also we have multiple ways of getting the square root and complexity. One such way is for I is equal to 0, I is less than some functions. Here we are starting at 0, going till square root of n. This is available in C and C++. Similarly, we can find the other functions in Java and Python or other leading programming language. It is clear that the overall running time of the algorithm is square root of n. The other way of getting the square root of n complexity is for I is equal to 0. Instead of comparing I with square root of n, we will be comparing I square with n. Here also the overall time complexity is square root of n, because we are executing square root of n times. There is yet another way of getting the square root of n complexity. Let us see that. I is equal to 1. In this code, I value is getting incremented every time, and that value we are adding it to s and comparing it with n value. Since we are not comparing the I value with n, definitely the number of iterations are less than n. But how do you find the exact running time of the algorithm? How do you analyze this code? Since we don't know the value of s at which we are coming out of the loop, let us assume we are coming out of the loop at kth iteration. In the first iteration, the value of I is 1, value of s is 1. In the second iteration, the value of I is 2. We are adding 2 to the current value of s, it becomes 3. In the next iteration, it will be 3, s will be 6, 3 plus 3, 6. It will be 4, 4 plus 6, 10. It will be 5, 5 plus 10, 15. It will be 6, 6 plus 15, 21. If you carefully observe the value of s, at ith iteration the value of s is sum of first I numbers. So at kth iteration, what is the value of s? Based on the series, it is clear that value of s at kth iteration is sum of first k numbers. So 1 plus since we are assuming at kth iteration we are coming out of the loop, at k iteration the value of s is this one. If it is greater than or equal to n, we are coming out of the loop. If it is less than, we will be in the loop itself. Since this is simple summation equation, k into k plus 1 by 2. Since these two are constants, we can ignore them. K square approximately greater than or equal to greater than or. So as soon as k greater than or equal to square root of n, we are coming out of the loop. Since we are assuming k is the iteration number at which we are coming out of the loop, the total number of iterations are order of k, which is nothing but order of square root of n in terms of n. Now let us take small variant of the same thing. If we add a for loop here, j is less than n, j plus plus, what would be the overall running time? As you already seen, the complexity of this one is log n, square root of n. And the size of this one is n. So n into n power 1 by 2. It will become n power 3 by 2. So the complexity of this code is n power 3 by 2. Similarly, if you add another for loop, it will be n power 5 by 2. So these are the common guidelines that we will be using throughout our discussions. And most of the fundamental algorithms fall in any of these categories. There are algorithms which does not fall in this category, but we'll be analyzing them with a different technique. But understanding these guidelines are very much important for the remaining discussion.